clock just changed, so we're recording now, everybody. And good evening. Linda, would you please go to the next slide, please? Okay, I'm just going to read some things here, and just some things that are on my mind. And Linda, at the outset, I'm going to mention something that one of the most students in our class suggested, and it actually was a good idea, but I don't want to spring it on you just tonight. I want this to be something that we think about. The idea that this student had was that after we do whatever the right number of problems is, they wanted to say, well, it would be good for us to just let them work on it for a while. Now, it's really easy to do in the classroom. It's a little bit more difficult here. And so what I'm going to ask Linda to ponder, and again, that was a very good suggestion the student made, and I'm glad they made it, but we have to think about how we're going to do this. Linda, I think we can create little groups or little rooms that we throw people in somehow, and we're not really throwing them in there, but they just sort of find themselves in there.
Yeah, we can do that.
Okay, and I almost don't want to do it necessarily in real time, but we'll think about doing that, and maybe we'll do that next time a little bit. Okay, so I want the student to know that I am thinking about what they said, and it might be a good thing. Now, one thing that's challenging though about this is when Linda and I are in the classroom, we can almost immediately tell if people are struggling, or if they're just romping ahead doing the problem or whatever, because we just can tell. We can tell just by looking around. We can't really tell by looking around you in some room. We might put people in rooms with like 2 or 3 other people, but then one of the challenges is how long do we have you work in there before we call you out and things like that. So Linda and I are going to be thinking about that, and just make a note of that, Linda, because we should think about some way to try that going forward. I want to think about how big the rooms are going to be and, all that. So I'm not going to try to solve that tonight. Okay. And I should have put that as a note here, but I didn't. That was top of my mind. Okay, I'm going to read a little bit. Midterm solutions will be published as videos. Okay, so that will happen. And also, pretty soon, I'm going to publish a low stakes assessment 8 video solution. Now, midterm solutions, although that'll be nice for us to do, I'm not assessing you on any more statistics, and so I think that's a nice thing to do. But the physics is going to be more relevant now, I suppose. So that means that the LSA 8 solution is going to be more relevant, because that's what we're going to be testing on. Tonight, I expect we will finish Chapter 1 and be moving into Chapter 2. And if we don't finish Chapter 1 tonight, that's okay. But I'm thinking that we'll probably finish Chapter 1 and move into Chapter 2. And I've been distracted a bit lately from making a whole bunch of extra videos for you guys, because I've been accommodating students for their midterms, and I'm grading their midterms and stuff like that. I'm not asking you to feel sorry for me, but what I am telling you is that soon, when all that is put to bed, which I hope is tomorrow, we're going to see more double time in this class, where there'll be videos that are being issued, and then we'll have the BCMs, and that'll all happen. And it's important, I suppose, for you to know that we're in week 10 now. Now we're at the beginning of week 10, but that's where we are. Okay, Linda, Linda, just so you're looking ahead here, I'm going to ask you if you have anything you want to say in a bit. Let's use one of these polls, just, how are you? And again, that could be great, okay, or, struggling, whatever. Linda is so ready for all this stuff. Wow. I'm very predictable, right, Linda?
Well, I mean, it helps when you have a slide that is kind of spelling everything out.
Okay, well, we're getting enough of a response here. I'm just going to say no one has, said that they were struggling, and a bunch of people said they were okay, and some people are, I don't know, maybe they're eating their dinner or something while they're watching this. Okay, so so I'm going to say okay, we're okay. I guess I didn't see any grades either, but this isn't Monday, but it's early in the week, so things will probably pick up. Linda, anything you want to say?
No, I think I'm good.
All right, that's fine. I always want to give you an opportunity to do that. Or that's my goal anyway. And are there any questions out there that anybody wants to pose? And we can try to come up with some answers. I'm not going to wait a long time for this, but if anybody's got anything they want to bring up, please feel free to do so. Okay, I counted to 5 or 10 or something. So I guess everybody's okay now. Now you are encouraged to ask questions, though, throughout the thing as well. Okay, now pretty soon, LSA 8, is pretty much in the bag. I have talked with a number of students in my office hours, and those have been some good, discussions and things like that. But we also have an LSA number 9. It's going to be coming. This comes from chapter 2. So Linda, I think the next slide is probably LSA 8, just reminding people of that. Let's see what it is. No, it's not. Oh, let's go back and talk about the bats anyway. I was thinking about bats earlier today, and I'm going to try to practice, doing some of these things we were talking about last time. Okay, this is a bat, and many people don't like bats, and especially women with long hair. Sometimes I find are saying I don't really like bats so much. Anyway, what happens is that bats use physics in their quest for prey, and it's called echolocation. So what they do to locate and capture an insect, these are mammals, they emit an extremely rapid series of bursts of high frequency sound. Now I was curious as to how high the frequency was, so I actually looked this up, and the frequency that bats talk at is around 120 kilohertz, or it's between 100 and 120 kilohertz. That means that's 1,000 hertz. Now, just to give you a little bit of a sense of that, human hearing is between, and maybe I guess I can do this too. Human hearing is between 0 and 20 kilohertz, 1,000 hertz. We're going to talk about what a hertz is later and everything else, but you see these bats are doing things that are way beyond human hearing, and so they're making noises that are 6 times the frequency that humans can hear, and that's good, because it would hurt us if we were hearing it, because they're broadcasting at an intensity of, I guess I need the pencil again, broadcasting an intensity of 100 decibels, and that is going to be a relative intensity, and that is almost as loud as a typical smoke alarm. Now, what happens when a smoke alarm goes off is you not only say, oh, there's a smoke alarm, I want to leave, you leave because it's almost hurting your ears. That's very near the threshold of pain for something to hurt your ears. So anyway, we're going to be talking a lot about that, and this is actually the very same thing that you're doing. So there's like a bug over here that the bat finds, and they send out these sound waves, and then the sound waves come back, and they know how far the bug is because they can process in their head, the time it took for this wave to get over there and to return. This is the very same thing you're doing with ultrasound. Now, the frequencies that you're using with ultrasound, though, we're going to see, this is a little bit of a look ahead, I guess. The frequency with ultrasound is going to be between 0 and 5 This is megahertz. That's a capital M, not a small m, a megahertz. So you see, so that is 6 times the frequency that we can hear at. This ultrasound is much higher than that. Is what's going on. So we're dealing with some very big numbers and that sort of thing. Okay, Linda, let's leave the bats behind us. This is LSA 8, and everybody should be making good progress on this and things like that. Let's go to the next one, Linda. And this is low stakes assessment number 9. And Linda, anytime I ask you to do something, there's always an implicit please there. Probably should always be an explicit please. But I'm going to ask you to toss this into the syllabus tab on both classes.
Okay.
And you can make up a target date for it and things like that. A week is more than enough, and we could do less than that. So anyway, let's just talk a little bit about what's going on here. And this is a graph. You have to deal with the graph, and this does. I think this is a really good problem. It deals with things that we're going to talk about in Chapter 2. Okay, so I'll start talking. The above graph shows the velocity. Now, velocity has units, and so the units on the velocity here are, we're going to see tonight that the units on velocity are going to be distance per time, and here it is feet per minute of a particle. You might say, wow, this isn't much of a particle, it's more like a bug. We could have called it a bug, it's just a thing. But this is the velocity in feet per minute of you could think about it being a bug or a particle, moving back and forth along a horizontal axis for 10 minutes. Now here's what that means. So you got a horizontal axis, so this is kind of like a tabletop or something. And this is, I just realized I could make lines instead of making bad lines like that. If I erase this, I lose everything, but maybe I haven't done anything worthwhile yet. I'm going to try this and see how this works. So did I get the line? I think I did. Okay. So what happens is, I don't know if that's that much better or not. But anyway, the bug is moving along a tabletop, and you see there are different places on the tabletop. There's a place that we could call 0. Oops, I have to go back and do something else. All right, so that could be 0, would be what that coordinate is, but if they go this way, it would be positive, and if we go this way, it'll be negative, okay? So, and what is going along this axis is, shows the velocity. So you see this is velocity up here, and that is as a function of time. So everybody should know that the y-axis here is velocity, because that's going to be important as you're solving this problem. So a particle is moving back and forth along a horizontal axis. This is what a horizontal axis means. And it does it for 10 minutes. Now you see this is time 0, and this is time 10 up here. So you see it's doing this for 10 minutes. It's going, back and forth along here. And let's see. That's good. So we know, how long it's doing that. We know that this is v of t, and this axis down here is t. So that's, I think that's probably good. Use the graph. So we have the graph. Your physics, you don't know calculus. You don't need to know calculus to do this. This is really a physics thing. Knowledge to answer the following questions. But you also should have your answer using correct units, because units are important in physics. So part A says, what is the velocity and acceleration at the time when t equals 1 minute? So you see, here's 1 minute, 2 minutes, 3 minutes, 4 minutes. And Linda, I don't know if that might be something that needs to be made a little bit bigger whenever you stick it into the thing, and you can make it on 2 pages if you want. I'll just leave that to you, or if it's good enough like this, we can just leave it like this. But anyway, the first question actually have 2 questions. It says, what is the velocity and what is the acceleration? Tonight we're going to learn more about velocity, and we're going to learn more about acceleration. But we're taking this snapshot exactly when t equals 1 minute. So we're saying when t equals 1 minute, what's going on? Velocity and acceleration. Now, I'm okay, and they'll say, well, I don't understand that yet. Well, no, we haven't had tonight's lecture, and we haven't had Thursday's lecture either, but you will understand that, but you also have to think about it some, okay? Now, assuming the particle started at the origin, we're telling you where the particle starts. Now, that's important because you have to know where it starts, and you might say, oh, it looks like it starts at 0. That's not what that means. That means at time t equals 0, the velocity is 0. So you see, this is additional information. So the particle starts at the origin, or 0, at exactly 10:13 a.m. So that is in the morning that this bug or particle is starting moving. Let's pretend it's a bug. That's a better story. At what time did the particle change direction? Now you see what will happen often with critters. They'll go this way for a while searching for food, and then they'll go back this other way searching for food. That makes this a vector, and we're going to talk about velocity being a vector, because even on a line like this, you could be going right or you could be going left. Okay, so they start at 0 at exactly 10:13. At what times did the particle change directions? Time should be exact and using seconds if required. Okay, I'm going to pause right here to ask if there's any questions anybody wants to ask, or and Linda, when I'm doing this, I'm really saying, is there anything you think that ought to be said here? Now we're going to go in and read these other parts too, but it looks like there's 5 parts and there's a bunch of questions here. Part A had 2 questions. Part B has it's kind of an open-ended thing. It says, when does it change direction? There might be multiple times. And okay, so I guess that's as far as we went so far. Any questions out there, or is it making sense to you, even though you say, I don't know how to do it yet? That's okay. Okay, let's continue then. Now, again, assuming it started at the origin, so it's starting at 0, 0 on this line that's going back and forth, what is the location of the particle at time t equal 10? So you see it goes for 10 minutes. So it's kind of like, you know, strolling here and strolling there and back and forth and stuff like that. I'm going to ask you, but this gives you information, this graph. So where's the particle when t is equal to 10? And that is 10 minutes. Okay, so that's up here. Where is the particle then? And it's not, you know, saying, oh, there it is. No, it's where is it on this axis? What's its coordinate when t is 10? Okay, part whatever this is, D, I guess. What is the average velocity and average acceleration of the particle or bug for the whole 10 minutes? So again, we're going to talk about velocity, we're going to talk about acceleration, we're going to talk about average velocity and average acceleration. And then part E says, at what time, and it does say times, so there may be only one time, or there may be more than one time, you don't know yet, is the particle the furthest from its starting point. So you see it started here, and it wandered off here a bit maybe, and then it wandered back, and so on and so forth. So when was it the furthest from its starting point? So it could be out here, or it could be way over here. And so you're supposed to get at that. Okay, the furthest from the starting point. And not just, see, this is asking at what times when. The other one is asking how far away from the starting point. Okay, so how many questions are there? Well, there is at least 1, 2. There's at least 3. There could be more than one answer there. Location when t equals 10, that's another one. Average velocity and acceleration. At what times, there could be multiple answers there. And how far from the starting point is it? So that's what we're doing. This is a nice problem. I like this problem a lot. And I think I really like that other problem, that brass washer problem that we did, because it really gets at a lot of things. So Linda will, you know, post this and make these things up, please. And we'll figure out, you know, when this is due and, you know, go from there. And that's an opportunity for you to learn. Okay, that is low stakes assessment. I guess it's 9. Let's go ahead, Linda, please. Okay, I think we started doing this problem last time, Linda, I think.
Yes, we did.
Okay, and I'm not sure how far we got. It's $1 billion worth of gold. And I think what I'm going to try to do is I'm going to, and we're not going to do all of this. Let's not do would it fit in a suitcase, but we'll figure out is a suitcase too heavy to carry. And I think this is an example in your book, so you certainly could read it in your book, or you could try that for, you know, some additional thought. So now, so Linda, the only thing I really need to know is it's $1 billion worth of gold. Now, what I'm going to do is I'm going to probably ask you again to, you know, look up some things. I know we did part of this, but we didn't finish this, did we, or did we, Linda?
We got close to. There were like one or two more calculations that we had to do to get the actual answer.
Let's move on then. I was not remembering how far we went. And Linda, I did not watch your video. So anyway, not that I'm sure it was worth watching, but I just didn't get that done. But here's another problem now. Okay, it's called tying up loose ends. Susie is wondering how long of a strand she could produce if she tied every hair on her head end to end. I think COVID has gotten to Susie, if that's what she's thinking about. But anyway, it's the problem. Okay. Now, I'm also going to tell you that I very rarely give multiple choice questions here, but there's some data here. And this one is, someone was giving me a courtesy smile there. They thought my joke was funny. Thank you. That was good. Okay. The average person has about 100,000 hair follicles on their head. So we'll just take that. And and the average length, or let's see, then what does it say? She uses the fact that the average person has about 100,000 follicles on his or her scalp to estimate that she went 20,000, she could do 20,000 meters. That's a long way, okay? That's about 15 miles, I think. And we could figure that is. It says, what's the average length of Susie's hair? And you have some choices here. And they do give you a cannot be determined. Let's just really think about that. Okay, so the total length then of Susie's hair, and Linda, if there's a calculation here later, I might ask you to do it. I don't know. We'll see.
Okay.
20,000 meters. And she tied her hair, all 100,000 hair follicles, she tied them together, and she ended up with this. Now there's 100,000 here, and there are, so this is 100,000. One, two, three, four. There we go. That's 100,000. Okay, 100,000 hair follicles, and the average length. We're talking about the length of Susie's hair. So this is 100,000 times L is equal to that. Okay, what I'd like. So everybody, if you have a calculator or Excel or something like that, let's do a poll here. So it's A, B, C, or D. Can we do a poll on this, Linda, please?
Yeah, absolutely.
What my student suggested. Oh, okay. So there was a question about the L. I'll talk about that. So we're going to remember back in the day when you did algebra, you would say something like let X equal something. I'm going to say let L equal the average length of Susie's hair. Length. I don't know if I should have typed that, but average length of a hair follicle. So see if she had, let's see, can I move that? No, I can't. That's all right. So if she had 100,000 times L is equal to the 20,000 meters. Okay, so this is not exactly what the student was, suggesting, but it's maybe getting at it a little bit. Okay, we're getting different answers. That's okay. Oh, some people think it can't be determined. Okay, well, we got some people, picking each answer, so that's good, and a little bit that. Linda, why don't you talk about, or do you mind talking about this one?
Sure.
Now, I don't know if I have to put my pencil away, or can you just jump up there with your pencil?
Yeah, I can definitely do that.
Right,
so remember that the average is the sum of everything divided by however many objects there are, right? So in this case, we have 100,000 hair follicles, and we have the estimate, the average, to be 20,000.
That's what the
so
average.
I believe
That's the sum of them all together, because you tie them all together.
So if you have 20,000 being divided by the number of hair follicles that you have, in this case 100,000, then when you divide those, you're going to end up with 0.2 meters. Now you'll notice that in all of these answers, then the units are in centimeters. So to change this from meters to centimeters, then there are 100 centimeters for every 1 meter. So if you do 0.2 times 100, then you end up with 20 centimeters.
Questions of Linda? Okay, and again, I probably would never, I don't know, I probably would never put this as a multiple choice question, but if I did, this could be a problem. And so, that's maybe a good example. Let's advance this slide, Linda, and see what else we have.
Okay.
I'm going to just talk a little bit about this. I am not going to stress significant digits in this class. This is called significant digits or significant figures, okay? But I think it's important that I tell you a little bit about these, because what happens is that there are rules, and physicists use these rules, engineers do as well. And so what might happen is, you might say, I thought I did this problem right, and they have a slightly different answer, or they might have a very different answer. So you see, if you took this number and multiplied it by that number, this is a rule of significant digits. I'm not making you memorize these rules or anything else. I'm trying to show you how things would be different. Okay, when numbers are multiplied or divided, the number of significant digits, and the result is no greater than the number in the factor that has the fewest significant digits. And so that is, this one has 5 significant digits, and this one has 3 significant digits. And so 3 significant digits is all you can have, and so you're going to get this. And Linda, I don't know if you have a calculator around or anything else. And by the way, this is a difference between physics and math. In a math class, if I took 2.1378 times 7.21, the answer is going to have 6 digits to the left of the decimal point. And in fact, Linda, if your calculator was nearby, what did you get for that? And I'll write it down up here.
15.413538.
0.41
3538.
3538. And you can see, as I prophesized, that's all the numbers you got, and that's the way you multiply decimals and stuff like that. But you see what's going to happen in the back of your book if you check answers or something, is they're going to have that. So just don't get upset or worried about that. These things will probably be significant digits. Let's talk about another kind of rule. when you add or subtract, the answer can have no more decimal places than the term that has the fewest decimal places. So for example, when you're adding these two things, this one has 3 decimal places and this one has 2 decimal places. So your answer can have at most 2 decimal places, and it's not going to have the 3 decimal places like Linda would tell you if we put this into your calculator. So anyway, there are these rules of significant figures. This is important for engineering things, and they'll use it in physics. We're not going to stress it. The thing I want to tell you is, if you're working on something, maybe you got this 15.4, all those numbers, you say, oh my gosh, they said it's this one. That's quite likely that, so I'm just telling you, don't worry about that. Let's move ahead, Linda. Okay, here's another problem then. We're just converting units here, okay? So at the German Autobahn, which is a high-speed highway in Germany, there is no speed limit. You can go as fast as you want, but they recommend that you don't go faster than 130 kilometers per hour. Okay, well, what is the speed in meters per second and in miles per hour? Now, this is what we call dimensional analysis or unit conversion. I'm going to ask everybody to give this a little bit of a go, and then Linda and I will work through this together. But what you want to be able to do this, and Linda, I guess we need some facts here for people to work with, don't we? So Linda, and I know, I'll tell you what, Linda, you have maybe, I don't know, is this hard for you or easy for you? Can you go and get a conversion factor for kilometers and miles, perhaps?
Yep, that's what I'm doing right now.
Okay, so she's going to tell me something. I'm going to write it down, and then we'll be good to go.
Okay. So for every 1 kilometer, and that is 0.621 miles.
Okay, so 1 kilometer. Actually, I'm going to try to do this. 1 kilometer make sure my fingers on the keyboard correctly. I think she said 0.62, did you say?
Yep, 0.621.
621 miles. Okay, everybody give this a go, and let's don't do both of these. Let's just do one of these. Let's change that to, wow, that's okay. No, we're going to do both of them. Let's do miles per hour first. Everybody do miles per hour first. And again, you got calculators and things like that. And Linda, why don't you just shout out when you think it's ready for me to write this again, and because we can't really look at how people are doing. We don't want to spend a whole bunch of time if people aren't making progress. So this is awkward a little bit today, but just shout out when you think we should be ready.
Okay.
Again, we're doing this one right here. I think that's the one I said miles per hour first.
All right, I'd say if they don't have it by now, then they're probably struggling.
Okay, so let's start talking about this then. All right, so I want to change this to miles per hour. So you see, I'm starting with 1. Oh, I'm in the wrong thing. Hold on. I'm starting with 1 kilometer. Then I'm multiplying that. This is like a multiply thing. And I need to multiply by that something, but I want to have miles per hour. And I'm starting with, this is kilometers per hour. Now you see, I'm in real good shape because I got that. So really the only thing we need to do here is change the kilometers into hours. Now this one is in the numerator, so I need kilometer in the denominator. So this is going to be, so per 1 kilometer, and I didn't make my K's the same way, but I'm not going to go back and fix that. And this is going to be 0.621 miles per kilometer. Okay, and so oh, I forgot where I was, Linda. This is 130 though. That was what I was going to do. I was going to change it to 130. So this is 130 kilometers per hour times, and Linda told us we know that the kilometer has to be in the denominator because we want to have miles per hour, and I did that again, made my thing look differently. But this is 0.621, I think Linda said, miles per kilometer. So this kilometer cancels with this one, even though they look different. And so we're going to take 130 times that. And Linda, you got a calculator, don't you?
Yep, I got 80.73 miles per hour.
You said 0.73?
Yep.
Miles per hour. Now I'm going to pause for a second in case there's a question about what we did. This is pretty standard, and we are going to do this other one too. We're going to go back and change this to meters per second in just a bit. Questions, or are we good? Okay, so I'm going to erase that, and boom, and it's gone. I actually like that, except whenever I didn't want to do that. Okay, so we'll go here, and we're going to be doing this. Now, this is 130. Again, Linda, you're armed with a calculator, I think, or Excel or something.
Yep.
So this is kilometers per hour. You see, we do need this. Now we want to change this to meters per second. So we got two things that we have to do. We have to change this to meters, okay? So we want the kilometers to cancel. So we're putting the kilometer in the denominator, but we want to have meters. So we know that this is 1,000, or I could call it 10 to the 3. Why don't I do that just for the heck of it here? It's 10 to the 3, and then this is meters per 1 kilometer. Now notice that this actually, since 1 kilometer equals this, again, these prefixes are something you want to know. Really, this is 1 because the top is equal to the bottom. So we're really multiplying by 1. We're not changing the speed of the car. And when I do this multiply here, I'll get some numbers. But the kilometers will cancel. And at this stage of the game, I have meters per hour. It's not what I want. I want meters per second. So we'll do this yet again. And when I do this again, this time I want the hours to cancel. So you see, I have to put the hour in the numerator because over here the hour is in the denominator. I want this to be seconds. And I really do have to think about how many. There's 60 seconds in a minute and 60 minutes in an hour. And I ran out of room, so I can't do all that right here. But that 60 times 60 is 3,600 seconds. So 1 hour is 3,600 seconds. So you see this unit of the hour cancels with that unit of hour. I'm going to do double strokes there. Okay, so we've got that. And so this ends up being our thing. So we have the right units now. It's meters per second. So we'll multiply all the way across the tops and all the way across the bottoms and divide and something. And Linda will report back to us. But I know that the units, based on my dimensional analysis, are going to be meters per second. So Linda, what did you get when you did all of this?
I got 36.1 meters per second.
Okay, excellent. Thank you. Now, later on when we talk about, a final exam or something like that, that's supposed to be 36.1. Later on when we talk about a final exam and stuff like that, Linda might say, well, I think there's a dimensional analysis. This is dimensional analysis that we're doing. They're changing units. That if she said that, and if I have something like that on it, this could be a problem. She says there's a vector problem. We know what that looks like, and so on and so forth. Okay, Linda, let's go to the next slide, please.
Okay.
Okay, Linda, again, I think I'm going to read this, but then I'm going to ask you to look up something. I think what I'm going to be asking you to look up is really two things: the speed of light, and the other thing. And why don't we? Well, we'll talk about this a little bit. Okay, but speed of light, and then Linda, the other thing I'm going to be asking you is the mass of an electron. Okay.
Okay.
And so you'll have that information, so I can throw this into the problem. Okay, here we will use the concept of significant figures in one of the most famous equations in all of physics. Einstein's theory of relativity predicts that mass and energy are equivalent. For instance, the energy E corresponding to the mass m of an electron is given by Einstein's equation, E equals mc squared, and I'm sure you've probably heard of that. But c is the speed of light, so that's what the c is, and we're squaring it there. And mc squared, so it says calculate the value of E, that is the energy, and we are going to be studying energy in this class as well. Energy is the ability to do work. We'll talk more about that later. For an electron, using powers of 10, and it says 3 significant figures. So we'll do that. Okay. So Linda's going to tell us things, and we went around to 3 significant figures. So I'm going to get up here and get the thing, and we'll start this. Linda, I'm just going to ask you things in a bit. Okay, so E is equal to, what was the mass of the electron, Linda?
9.11 times 10 to the negative 31st power.
Now this is like really tiny because it's 10 to the minus 31, and Linda's going to tell us units too.
Let's see. That is kilograms.
Because it's mass, and it's either kilograms or it could have been grams or something, but it is kilograms. So that is really good to know. So that's what m is. Now Linda is going to tell us the speed of light.
You want 3 significant figures?
Yeah.
All right, then that would be 300 million meters per second.
Let's see, 1, 2, 3 more. Okay, and let's see. Oh, I got to be careful. I can't erase that. Okay, and that's of course meters per second, right?
Yeah.
Okay. And that's squared, isn't it, folks? Okay. So now what you're supposed to do is, and I didn't leave much room here, so maybe I should ask Linda to do this. No, I'm kidding. Certainly you could do it, but okay. So I'm going to ask everybody, and we're not going to give you a lot of time. Linda will, figure out when we want to call it quits on this. We're supposed to use powers of 10 and 3 significant digits. Okay, so so go, and again, don't worry, just leap in and give it a go. I'm going to talk a little bit about this. Linda, let me know when you think we've given enough time for students to do it, please.
Okay.
Okay, well, and I will talk just a little bit about that. But you see, the question was, what unit should this be? And in fact, there are units that are called joules. Okay, so I'll talk a little bit about that too. And we're actually covering more ground than you might think, because some of these things are kind of a look ahead. but just we're going to. I will speak to that, Paula, as we do this. So, but well, I'll just tell you what's going to happen here. What we're going to get is kilogram meter squared divided by second squared. Okay, now I'm going to talk about other names for these in a bit, but that's what it's going to be. It's going to be kilograms meter squared per second squared. You might think, oh my gosh, that's confusing, but we'll talk a bit about it. Linda, are we ready to go, you think?
Yeah, they should be done by now.
All right. Now, this one is 3.00. I could put more zeros here if I wanted, times 10 to the. Okay, so you see it's 1, 2, 3, 4, 5, 6, 7, 8. So that is times 10 to the 8th. And this is 9.1 times 10 to the minus 31. Okay, so Linda, when I take 3 times this, well, let me do the powers of 10 first, okay? So when I take 10 to the minus 31 times 10 to the 8th, you add the exponents. I get that as 10 to the minus 23. Let's see, this times this is going to be 2733, right?
Did you square the 300 million?
No, I didn't do that at all yet, and I should have squared that to start with. Yeah. Okay, so so when I square that, I get 16, and so now this is not going to be, and I have to erase all of it, so I'm just going to scribble through that. So this is going to be 10 to the. Linda's fixing that down there. Thank you, Linda. Okay, so that is going to be 16, and that is minus 15. So this is 10 to the minus 15. And then to 3 significant digits, let's see, when I squared, I got 9. 9 times 9, that's 81.99.
Yeah.
Okay, so that's like 82.0, I guess, if we rounded that to the nearest 3 digits, and that's times 10 to the minus 15. And now I am going to talk a little bit about units here, Paula. And by the way, this stuff will make sense by the time we're finished with physics. It might not make a lot of sense now. And by the way, if you were to write this a different way, you could call this 8.20, which is really the in scientific notation, because we'd have one thing here, and then this is going to be times. And let me think about this. I divided by 10, so I have to, let's see, so I divided by 10 there, so I multiply by 10 there, and so that is minus 14. And now I'm talking about the units. The units here are going to be kilogram, meter squared per second squared. Now, and that is the raw units there. But this is the same thing as saying kilogram meter. That's the product of kilogram meter times another meter. That's a multiply over second squared. Now, what we're going to learn very soon, and we got to get to this now, but you see, this thing is going to be called later. That's a unit of work or a unit of force, and that is called a. It's going to be called a. Well, let's see, kilogram. Let's see, how do I want to say this? This is going to be a. Actually, I guess we're going to do it. Okay, so kilogram meter, and that is so it's M A. So it's mass times acceleration. Anyway, this is going to be what we call a Newton meter, we call this a Newton. And we did do a vector problem with Newtons. We just didn't know what they were yet. They did that in chapter 1 out of this book. But this is the Newton. That's a meter. So you see this ends up being what is called a joule. And a joule is the unit of energy. Now, Paula might be thinking, well, boy, this is confusing. And and Josh will be with you in just a second. And it can be confusing. I'm not talking about stuff we're going to be doing. And so we're just, right now, we're practicing mostly with these. Josh, what's on your mind?
A joule is the same as Newton meter? Is that what you're saying?
Yeah.
Okay.
But we'll talk about that in a bit. Okay. I mean, seriously, we will.
I've heard both the terms. I just didn't know they were interchangeable.
Yeah, they are. And Joule was, well, Newton, of course, was a Newton, and Joule was a great physicist also, and he did a lot of work in heat conduction and stuff like that. Okay, Linda, let's go on to something else. I think I'm tired of this, I think.
Okay.
Let's go to something else. The age of the universe. I'm not going to ask you to do this, but here's an example problem that's in your book, and you could do this, okay? So it says, oh, the universe is, let me grab this, the universe is 13.7 billion years old. How many seconds is that? Our species, I guess that's Homo sapiens, evolved this many seconds ago. How many years is that? So you see, there's all kinds of problems like this for you to practice. Let's advance the slide, Linda, and see where else we go. Here's a couple of problems. Trying to think if I really want to do this or not. I think I'm not going to do either one of those, but those would be good problems for you to think about. And certainly you could ask questions about those if you thought they were hard. And so, I mean, just there's some examples. So Linda, let's go. I think I want to start talking about the next chapter soon. Hey, right here. Okay. Now, so we're going to start talking then about, we really haven't talked about velocity yet, but you're interested in that because the low stakes assessment does this. Okay. So this talks about velocity and acceleration. This corresponds to these sections in the book, but I'm just summarizing stuff. So when an object moves along a straight line, and by the way, we are moving along a straight line. We describe its position with respect to an origin by means of a coordinate such as x. See, it's a straight line. You see that just moving back and forth might as well be the x-axis. So if you start at point x1 at time t1. And by the way, physics is great about using these subscripts. So x sub 1 corresponds to t sub 1, and it arrives at another point, which is called x2 at t2. The object's displacement is a vector quantity. Now, the reason it's vector is, even you're on a line, you can be moving in the plus direction or the minus direction. So it is a vector quantity, and it's important that you remember that velocity is a vector. We'll study a lot of vectors, and so we'll have that. The object's displacement is a vector quantity, and this terminology, delta x, often means the change in x. That is x2 minus x1. So there's a lot of notation here. Okay, but the displacement doesn't depend on the details of how the object moved. If Linda were leaving Warrenville and going to the Jewel food store or something near where I live, she would go there, and if I were in Warrenville and I were going to that Jewel food store, we both would be traveling the same distance if I was, leaving from wherever she left, but she might drive much faster than me, or vice versa. Okay, so we talk about the average velocity then. The average velocity is given by this equation. By the way, the average velocity is talked about in your problem. So now, and again, I'm sorry about the notation, but this is the way it is. The velocity, this is the average velocity, and that means it's in the x direction, is x2 minus x1 all over t2 minus t1. Once upon a time, I worked in Indianapolis, but I lived in Wheaton. And Wheaton is like here, and it's not exactly north of Indianapolis, but it's kind of like this. So I was going pretty much south to get to Indianapolis. And in fact, I knew from the time I left my door till I got down here, was 210 miles. So you see that's the distance. The distance from my house at Wheaton to this was 210 miles. So I took the difference in the x coordinates, and then I divided this by how long it took me. And usually it took me, or let me say it another way, on a good day, it took me 3 hours. So Linda, what was my average speed?
That would be 70 miles per hour.
Exactly. And you see, if you think about this for a while, if I average 70 miles per hour, I'll just ask Linda, Linda, do you think that I, backed out of my driveway, put the car on cruise control at 70 miles per hour and turned on my
Probably
tuner?
not.
No. And so when that lady, state trooper in Indiana, stopped me, she probably was stopping me for a good reason, because I had to be going over 70 miles an hour during some of that time to average 70 miles an hour. Okay. And in fact, she told me, and by the way, I tried that. I said, no, I was not going over 70 because it's 210 miles and it takes me 3 hours. And she said, at 11:06 in the morning, you were going at, and I won't even tell you what that speed was. It was a very expensive stop. So anyway, that's what's happening with velocities. It's a vector quantity, and we have that. Linda, let's go to the next slide, please. Okay, acceleration is something different. See, acceleration is this. So you see, velocity is the change in position over the change in time. I went 210 miles over a change in time. Now this is acceleration. This is the change in velocity. So the acceleration in the average acceleration in the x direction, again, directions matter, and they are talking about acceleration is the change in velocity. So this is v2 minus v1 in the x direction divided by t2 minus t1. And a story I often tell is that if my daughter Beth were on Naperville Road and she was getting on to, I'm actually not drawing this the right way, but this is the east-west, maybe I'm drawing this almost okay. This is here's Beth coming along like this. She's going whatever the speed limit is on Naperville Road. Let's just say it's 40 miles an hour. I don't know what it is for sure. It's 40 miles an hour, but she's going to get on this tollway. Well, what she has to do is she has to go from her 45 mile an hour speed to, when she merges in traffic, she has to be going much faster than that, at least 60, and maybe faster than that. That's acceleration, because she's starting here going, let's just say it's 45 miles an hour. Let's say she gets up here, that is 70, and she spends 2 seconds. Then what she's doing is 70, because that was her final velocity, minus 45. It's going to be 25 in a bit. Okay, and that is going to be miles. That's the change in her speed, in her velocity. That's miles per hour. But then let's suppose she spends 10 seconds doing that. I don't think she'd spin that long, but anyway, that's the way I'm writing it. 10 seconds. So you see, this is going to be miles per hour. So you see, that's miles per hour up here. This difference is 25 miles per hour. Linda probably has a calculator. Over 10 seconds. Oh, I said miles per hour in seconds. 10 seconds is, let's suppose Beth spins. She's not spending 10 seconds doing that. She's doing that in point.
Well, 10 seconds is 1/6 of an hour.
1/6 of a minute, right?
Yes.
Second. Okay.
So
36.
Yep.
Yeah.
So I'm getting 900.
Okay, so she got 9. Wow. Okay, so Beth is really accelerating. But my point is, this is going to be miles per hour squared or meters per second squared or something. So the units here are going to be distance, meters over seconds squared. Okay, so that's acceleration, and that's also in the problem you're studying. Linda, let's go ahead and advance the slide.
Okay.
And we're going to do more things on Thursday. Let's do a problem, Linda. Let's go ahead. I don't want to go into just all these equations, so keep going. I'll stop you in a bit. Keep going. Keep going. We're finished with chapter 2 if we did this. Okay, let's go ahead. We'll come back to this one. Let's go ahead, though. I'm looking for. Here we go. I'm going to read number 8, and we're going to work number 8 because I think it's better working problems to nail some of these things down. Okay, this is a family trip. Okay, so I know I'm just reading to you guys, but I like to read. You and your family take a trip to see your aunt who lives 100 miles away along a straight highway. The first 60 miles of the trip are driven at 55 miles per hour. Apparently, you're just setting, that's the average speed, or you set this on cruise control. Then you get struck in standstill traffic for 20 minutes. In order to make up time, you then proceed, this is me, you then proceed at 75 miles per hour for the rest of the trip. Here's the question. What is the magnitude of your average velocity for the whole trip? By the way, this is a one-way trip. So you start at your house and then you go to see your aunt, and it's 100 miles away. Okay, so Linda, I don't know if I'll memorize those answers or not. Can you, let's see.
I got the numbers.
You got the numbers, good. Give me a whiteboard, please.
Okay.
Oh, wait, maybe I could just do it here. I'm going to try to do it here. Oh, okay, I got this. This is good. Okay, all right, so what happened? Well.
So it is a 100-mile trip.
I'll tell you what, Linda, you want to just do this problem? Go ahead.
Sure.
All right, go ahead. And I know you have numbers, but go ahead and do it, please. I want to share.
So for this 100-mile trip, then first we start for 60 miles going 55 miles per hour. So that is for 55 miles per hour. And then we're stuck for 20 minutes. So we go 0 miles. And then we do 75 miles per hour for 40 miles. So we're finding the average velocity. So to do that, then let's see, average velocity would be change in velocity
change in distance
over change in time.
Yeah, change in distance over change in time. That's the average.
Okay.
Yeah.
So then to figure out how far we're actually going during each chunk of our journey, then I'm doing 60 miles. That is times 55 miles per hour. And then I believe we're adding 40 miles.
Linda, I'm going to draw a picture just here too to help the students think about this a little bit. Okay, so you went from, and again, I'm giving this back to you in just a minute. All right, so we're starting at, and Linda never knows what I'm going to do, and it probably drives her nuts. But anyway, we go up here. So we went 60 miles, and this is where we hit the traffic jam. And we know we've got to go 40 miles the rest of the way to get to, it's not grandma's house, it's auntie's house. Okay, so there we are. So you see, we know we're going, so we know the change in distance is going to be a total of 100. Okay, but how long did we spend here? I'm going to call that T1. And we also lost 20 minutes being stuck there. Then how long did it take to go T2? So you see what Linda's doing is, she's saying the change in distance. Now that's going to be 100 just because that's how long it was to get to grandmother's. But now Linda is going to be calculating T1s and T2s and adding them to 20 minutes. And she's got to be a little bit careful because that's going to be minutes and this is going to be hours, I think. And Linda, I'm giving that back. I just was trying to draw a blue picture.
Yeah. I think I actually need to switch my units on this.
Okay.
Because if I'm trying to figure out how many hours this is taking me, then I want the miles to cancel. So I believe I'm actually doing 60 miles, and then that would be times 1 hour over 55. And then
Right.
we don't go, sorry, what?
Right, good, yes,
Okay.
yes. And that in my picture, that ends up being, I guess, that's T1 in hours, isn't it? So what do you get, Linda, when you do that? It's a fraction, it's a little bit over an hour, isn't it? But it's, let's
Yeah.
see, go ahead and pound that in a calculator and we'll get that. I'm blue canceling those for
Okay.
Linda.
So I'm getting 1.09.
So that's 1.09. 1.09 hours is there. Now, 20 minutes is a third of an hour, so that is another 0.33. And then T2, Linda. Out T2, we're going, I guess that was, or no, yeah, that is T2. We went 40 miles, but we were going at a speed of.
So that was 75 miles per hour. So then I would
Yeah.
multiply that by the 1 hour for every 40 miles. Actually, just the 40 miles on the bottom.
Yeah.
No, I
Actually,
totally switched these.
yeah.
So 40 miles and then multiply that by the unit. So 1 hour for every 75 miles.
Yes.
So then 40 divided by 75 gives me 0.53.
Okay. Okay, so Linda adds those numbers up, and we know how long it took us. So what's the time, Linda, then?
So I'm getting 1.95 hours.
Okay, that sounds good to me. And then
And it asks for minutes.
you have to do 100. Or wait, what the problem asks us to find? Our average velocity. Right.
Okay.
The distance is 100 miles. It took us 1.95 hours. And
Okay.
figuring out what that is. That's going to be
So I'm
around.
getting 51.3.
Yeah. Okay. I'm going to try to answer Paula's question. She was asking where the 0.33 came from. This was, Paula, up here, this was 20 minutes. There's 60 minutes in an hour. So that's like a third of an hour, and a third of an hour is 0.33. Now, Paula asked a good question, but you got to really, really, really think about your units. It's important because you see this change things. And you might say, well, gee, you were going 55 miles an hour, then you were going 75 miles an hour, and now you end up, that's your average speed. Yeah, but don't forget, you were stuck for a while. Paula, did I answer your question? Good. Okay, thank you. All right, and by the way, I never not want to answer your questions. If I don't do it or don't do it well, please ask again. Okay, any other questions of me or Linda on this problem? I like this problem. It's a good problem. Okay, let's go look at something else then, Linda.
Okay.
Back to the PowerPoint show. I know what time it is, everybody, so don't worry. I'm not lost. Or if I mean, I know what time it is at least. Okay, so she's getting a PowerPoint thing up there in a bit. Okay, that's really good. Okay, and that was the family trip thing. If you want to try a different problem, here's one dealing with a supersonic. I guess they say hypersonic jet plane and stuff like that. So there's a lot of problems here. So that's good. Okay, let's go back in time with the slides. See what else we've got. Okay. That's a bridging problem. We are going to do that. We'll do that next time, but keep going back, please. And that's relative velocity. That's free-falling objects. Keep going back there. Okay, and I think that's where we want to be. Okay, yes, so we talked about velocity, we talked about acceleration, so Linda, go forward a slide then. Now, there can be motion with constant acceleration. That means it is a steady acceleration. An important example of that is if you went to the top of the Berg Instructional Building and dropped a bowling ball off it, and given that everybody is sheltering in place, no one would get hurt except the bowling ball. If you drop that, there really is a constant acceleration, and we call that the acceleration due to gravity. People call that G. There'll be a lot of these problems that talk about G. And G is, it's an acceleration. So G is, and it depends on what physics class you're in. In our class, we're going to call this 9.8. And this is going to be meters per second squared, because that's a unit of acceleration. And remember, it's a change in velocity divided by time. So you see you got meters per second, which is going to be meters per second squared. And it is a vector. And this one is going down. You have to keep track whether you're going down or up and what you're doing, because it is a vector. Okay? But that's an example of constant acceleration. And I, in that little problem I was invented, I said, oh, my daughter Beth, she's doing constant acceleration on that ramp as well. Okay, so here is something that's true. Since the change in velocity divided by the change in time is equal to acceleration, you say that Vx minus V0x is equal to A times t. So you see the velocity in the x direction is the initial velocity I'm going plus the acceleration times the time that I'm accelerating. Okay, so this is a nice equation that you'll use. Now, we will have this available for you, but you have to know what is it good for. Okay, and since the change in distance over the change in time is equal to velocity, and what we can do is that's supposed to be a change in distance, so x minus x0 is equal to, I take t times v, but this would v, so actually I get that equation. That's another equation. Now, this equation talks about finding the velocity. This equation talks about finding the position. And I could ask you, except it's getting very close to our closing time, so I'm not going to, burn some time here. There's a big difference between this equation right here and this equation right here. The big difference is time is in this equation, and there is no time in that equation. So we're going to be using these equations a lot next time to study problems like that bridging problem that Linda was talking about. Now, I really think we covered enough that you could probably start making some progress on that low stakes assessment. But you're going to be better at that when we come back next time. Linda, let's just go a little bit ahead and look at maybe a problem or two. And so we're advancing the slides again. I do know what time it is. We only got like a minute left. Going. This was up and down. Keep going. There's a bridging problem. We'll do that next time. There's the family trip and jet. Here's a good problem. I like this problem a lot. I'm just going to tell you a little bit about this problem, then we'll be done. I don't know. I will tell you a story when I was a kid, and students don't like my stories, I know. This really happened to me. I had an electric stove, and I walked into this stove, and I put my hand on the burner. And do you know that I put my hand on the burner, and I said, oh, damn, I bet that's hot, before I felt any pain. The reason I did is that nerve impulses travel at different speeds. Touch travels at this speed, and pain travels at that speed. So you see, I knew I touched that burner before I started hurting. I don't know if you've ever had that experience or not. If you stub your toe, you'll say, damn, I stubbed my toe there, and then you feel the pain. So anyway, here's a problem, and we might do this one next time too. For now, time is precious. Each day must count. Do the math, it will make you strong. We're somewhere in chapter 2 now. Take care, folks. I'll have office hours at, I guess, 7:30.
Thank you. Have a great evening.
Yeah, you guys too. And Linda, you're recording this and everything, and I didn't dump too much on your plate, did I?
Nope, you're good. I'm stopping the recording now.